List the three different ways the negative numbers can be represented in binary. We have three different ways to represent a binary number, negative binary number, unlike normal representation. The three different ways are: one, signed magnitude method. The second one is one's complement. First method is signed magnitude. Second one is one's complement. And the last one is third one is two's complement. So these are the three ways to represent a negative number. So now let us see how to represent a number using signed magnitude method. In signed magnitude method, whenever we have a negative binary number in the signed magnitude method, whenever we have a negative binary number. For example, let us take the number minus 12 in decimal. To represent this number in negative, in binary form, we have to, by using the sign magnitude method, firstly we have to write the binary code of 12. We have to write the binary code of 12 in 8 bits. Let us write the binary code 1, 2, 3, 4, 5, 6, 7, 8. So the binary code of 12 is 0, 0, 1, 1, 0, 0, 0, 0. This is the binary code of 12. So to represent the binary code of minus 12, we have to take the most significant bit as 1. For a negative number in binary code, the most significant number is 1. For a positive number, it is 0. So always for a negative number in binary, we'll have the most significant bit as 1, and for a positive number, we'll have 0. So, so to represent this 12 in negative, in sign magnitude negative number, so represent minus 12, we have to take the most significant as 1 and the other binary representation as it is 0, 0, 1, 1, 0, 0, 0. So this is the sign magnitude way to represent a negative binary number. Now let us discuss one's complement method. Second way, one's complement method. In the one's complement method, we take, again we have, for example, we want to write the binary code for minus 12. So we have to take the normal binary code of 12 first, that is 1, 1, 0, 0. Let us take the most significant bit 0 because it is a positive number. It is the binary code of 12. Now to represent minus 12, in one's complement method, all the ones should be written as zeros and zeros should be written as 1. So to make this number in the one's complement method to minus 12, we have to take all ones as zeros and zeros as 1. So 0, 1, 1, 0, 1, 0, 1, 1. This is the ones complement method way of representing minus 12. This is the binary code for minus 12. So let us discuss now two's complement method. In two's complement method, Two's complement method is nothing but taking one's complement and adding 1 to it. One's complement method plus 1. So we are again will take the same example. 2 12 minus 12. So firstly we have to take its ones complement. Firstly let us write the code, binary code for plus 12, which is 0 1 1 0 0. Now the ones complement of 12, that is the binary code of minus 12, is 1 0 0 1 1. Now for 2's complement we have to add 1 to the ones complement, that is nothing but 1 0 0 1 1 plus 1 1 plus 1 0 carry 1 1 plus 1 0 carry 1 1 plus 0 is 1 0 as it is and 1 as it is. In this again the last, that is the most significant bit, is 1, that is a negative number. It is representing a negative number. Always in all negative numbers the most significant bit is 1. So 1 1 0 1 0 0 is the two's complement way of representing minus 12, that is the binary code of minus 12 in two's complement method. Now let us go to the next problem. Uh, Find the Minterm designation of the following: x, y, z, x complement, y complement, y, z complement, and x, y, z complement. Minterm. What is a minterm? Generally, we represent uh, our expression in Boolean function form. Boolean function form. Minterm is nothing but a canonical form. Canonical form in means in Boolean algebra, a Boolean function can be expressed in two ways. A Boolean function, that is, can be expressed in canonical form. Canonical form consists of two forms, that is minterm and maxterm. Minterm means nothing but a product, and maxterm means sum. Now let us see about canonical form minterm. In minterm, we take the product of the terms, and in the minterms, the product of the term should finally give us 1. We have to get 1. We look for the functions where the output is 1. A minterm, each of its terms should have 1, and then we take the AND operation of it. For example, if we are taking x, y, z, a minterm of the function which consists of x comma y comma z, Then if x is equals to 1 and y is equals to 1 and z is equals to 1, then the minterm will be x into y into z. This is the minterm. Now let us see how we can represent different minterms when we have different values for x, y and z. X, y, z. Let us see minterms. This is nothing but product terms. Now let us take the different inputs we can give to x, y and z. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. And we can also have 1, 1, 1. Now for min term of this expression 0, 0, 0. Since x is 0, y is 0 and z also is 0, to represent its min term we should have each of its term as 1. So to get 1 we take its complement, that is x complement, into, since min term is nothing but a product, into y complement into z complement. This is M0, zeroth minterm. Now in the second case, similarly, to get minterm where x is 0, y is 0 and z is 1, we have to take complement of x, so it is 1, complement of y, so it is 1, and z as it is because z is already 1. So finally here we will get 1. Each of the minterms finally we will get 1. This is zeroth minterm. This is first minterm. Now second. And here we have x is 0, so we take x complement. We have y 1, so we take y as it is. We have z 0, so we take z complement. Next case. Here we have x 0, so we take x complement. We have y as 1, so we take as it is. We have z as 1, so we take as it is. So x complement yz is the third minterm. That is because x is 0, y is 1 and z is 1. If we take this as a binary code, then we will get 3 for 0, 1 and 1. That is why the third minterm is x complement M3. We get x complement into y into z. Now fourth minterm. Binary code 100 represents 4. So 4 minterm is, we have x as 1, so we take x as it is. We have y 0, so y complement. We have z 0, so z complement. Next, 101 represents 5. So fifth minterm is, we have x as 1, so x as it is, into y as 0, so y complement, into z as 1, so z. Next, 110 is binary code for 6. So M6 is X as 1, so we take X as it is, Y as 1, so we take Y as it is, Z as 0, so we take Z complement, so that the product is 1. The last case, M7, 111 represents 7 in decimal form. So the minter M7 is X as 1, so we take X as it is, Y as 1, so we take Y as it is, and Z as 1. From this table, in the given question, we can write the minterms for all the three given terms. The question is find the minterm designation of the following. First question, he gave X into Y into Z. X, Y, Z represents that X is 1 and Y is 1 and Z is 1. So the product is coming as 1. So it represents the seventh minterm. So we write M7. Second question. He gave X complement into Y into Z complement. So here X complement represents Y. So X value is 0. Y complements represent 1. We all the terms in this should be equal to 1. X complement is 1, so X is 0. Y complement is already 1, so Y is 1. Z complement represent 1, so Z is 0. So 0, 1, 0, we get binary code as 2. So X complement Y Z complement represents the second minterm, which is M2. You can also verify from this table X complement into Y into Z complement is M2. Now let us solve the third question in a similar manner. The third question is X into Y into Z complement. Here each term again represents 1. So X is already 1. So it is 1. Y already indicates 1. So Y is 1. Z complement is indicating 1. So Z is actually 0. Now 110. The decimal code for 110 is 6. So this is the sixth minterm. XYZ complement, you can also check from the table, that is nothing but the sixth minterm.
Uh, our question is to convert a given binary code to a gray code. Okay. So, for converting a given binary number to gray code, we follow few steps. Suppose we have a 4-bit binary number, for example, say 1011. We need to convert this into gray code. The first step in converting a binary number to gray code is to keep the most significant bit as it is. That is, see, this is the binary number. Let me represent it as B. Next, we are keeping the most significant bit as it is. Now, the second digit of the binary number is XORed with the first digit. That is, the second digit is XORed with the first digit. So now the third digit is XORed with the second digit. Similarly, the fourth digit is XORed with the third digit. So the final gray code will be 1, that is keeping the most significant bit same. 0 XOR 1 represents 1. 1 XOR 0 represents 1. 1 XOR 1 represents 0. So this is the final gray code which we get. Basically, in converting any binary code to gray code, we use XOR operation. Converting from binary to gray, we use XOR, and vice versa. That is, converting gray to binary also, we use XOR gate. What? And in a XOR gate, if there are two different inputs, then we get the output as 1. And if there are two similar inputs, we get the output as 0. That is, the truth table for a XOR gate is somewhat this way. That is, take a two inputs, that is x, y. Let this be the output. We have 0, 0, 0, 1, 1, 0, and 1, 1. Now, in a XOR gate or XOR operation, two similar inputs will give the output as 0. That is 0 plus 0 XOR 0 will be 0. Two different inputs will give output as 1. That is 0 XOR 1 is 1. Similarly, here there are two different inputs, that is 1 and 0. So the XOR operation will produce the output as 1. And here 1 XOR 1. So these two are similar inputs. So the output will be 0. This is for XOR gate or XOR operation. Now, so this our question. The question given to us is convert 1, 1, 1, 0 to its gray code equivalent. Gray. This is a binary number, so we need to convert this into the gray code. So let us follow the steps which I have discussed earlier. So we'll take the given binary number 111 and 0. The first step that we need to do is to keep the most significant bit as it is. To keep, then we the second digit is XORed with the previous digit. That is, this second digit is XORed with the first digit. That is 1 XOR 1. Similarly, the third digit is XORed with the second digit. 1 XOR 1. Finally, the fourth digit is XORed with the previous third digit. That is 0 XOR 1. So our final gray code is 1, 1 XOR 1. Two similar inputs. So the output is 0. Two similar inputs. The output is 0. That is 1 XOR 1 is 0. Two different inputs. The output is 1. So our final gray code is 1, 0, 0, and 1. For verification, there is a simple trick. So, to verify that we have converted the given binary number into the gray code correctly, there is a simple trick. So, the given binary number to us is 1110. Now, uh, we need to add the first three digits, that is 111, is being added to this number. So, now the most significant bit remains the same, that is 1. So now perform simple binary addition to these two numbers. That is 0 plus 1 is 1. 1 plus 1 is 0 and 1 carries. We are not going to add any carries. We are just retaining the sum part. So here also 1 plus 1 is 0 and 1 is carry. Since we are ignoring the carry, the number is 0. So this is the required gray code. Did we get the same one? Yes, we did. So this is conversion of binary to gray.